Okay. Thank you, Iman, for the introduction. I'll try to get things going. Okay. Okay. So today I'm going to talk about asynchronous distributed optimization via door decomposition and block coordinate ascent. So this is joint work with my PhD supervisors, Dragan Nesic and Iman Shames. So there are four main parts of my talk. First, I'll introduce and motivate the problem. And then we'll present the algorithm, which is based on door decomposition, and it's a distributed algorithm. And after that, we'll analyze the convergence properties of the algorithms. And finally, we'll conclude our work and give some future research directions. So first, the introduction. So nowadays, many systems are large scale and they're networked. For example, in parameter estimation sensor networks, and it can be formulated as an optimization problem. So it's basically a large scale optimization problem. And in distributed MPC, especially in economic MPC, you may have cost functions that are not strongly convex, but are convex, which is handled in our work because in particularly different from other work is that we do not make assumptions like strongly convex cost functions like most works in the current literature. We only assume convexity of the cost function. And the next one is machine learning, especially in large scale problems. You may also have some regularized problem that may make the cost functions non-smooth. Again, since this is a door based on door decomposition, we're not making the assumption that the function is smooth, let alone having Lipschitz continuous gradients. And although they will help improve the properties of the algorithm, but we're analyzing the general case of the algorithm. So a general setup of distributed optimization problem is that you have a group of agents that cooperatively solve an optimization problem, so that agents have their own storage units and they perform computations locally and they communicate to their neighbors to collaboratively solve an optimization problems. And in large scale problems, synchronization may be costly. So that's why we are interested in analyzing asynchronous algorithms in these distributed optimization problems. So here is the mathematical problem formulation. So we're trying to minimize a finite sum of functions fi with its argument xi, and the global decision variable x is constrained in this calligraphic x and subject to some equality constraints. Here fi, which is convex, and we are not imposing that it's smooth, so it's the cost functions. And the matrices Eij and Eji are just selection matrices indicating the coupling between local variables. So if you are familiar with the optimal consensus problem, if you take all of these matrices to be identity, then it becomes exactly the same as the constrained version of the optimal consensus problems. But in general, they don't have to be identity, so they can be partially overlapping. And here, the big calligraphic X is the convex constraint set. At this stage, we're not imposing that it's compact. We're just assuming it's convex. So that's the problem formulation. And what we mean by distributed optimization. So since we have a sum of n functions, we're going to employ n agents connected via a network described by a non-directed network, by a non-directed graph. So this means that if agent I can talk to agent J, then agent J can also talk to agent I. So they can share the necessary information with their neighbors. And each agent only has access to its local objective function fi and its local decision variable xi. So they don't have any information unless someone decides to transmit it to it about other agents. So it's particularly interesting in the interest of privacy. And agents can perform computations locally and communicate necessary information to their neighbors. And this information depends on the coupling of the problem. So agents only transmit necessary information to their neighbors. They don't have to transmit all they have. So for privacy reasons, this is particularly interesting. So some existing works on distributed optimizations. So there are many of them since the 80s, and it's still exponentially growing, and there are just simply many of them. And I put them in three categories. The first one is primal methods. So I list two examples here. Probably the best known one is the consensus-based method. So you design an algorithm which is just a combination of a consensus algorithm and a subgradient or gradient step. And under some assumptions, some mild assumptions on the step size and the connectivity of the graph, you can show convergence to, you can show either exact convergence or convergence to a neighborhood of the solution. And of course, you can do second order methods like the Newton method, following similar idea. And the next one is dual methods. So the idea is we formulate the dual problem and solve the dual problem. And if there are no duality gap, then we also recover the solution to the original problem. And ADMM that's alternating direction method of multipliers. So it's using the same idea, but it's using a slightly different formulation from what we're going to talk about today. And the third one is asynchronous method. For example, if you know block coordinate descent, so that's you have an optimization problem that's only updating a subset of your components of a decision of your decision variable, so that they don't have to be synchronized. And today we're gonna the algorithm we're gonna talk about also borrows idea from this method. So if you're interested in if you're more interested in this work and you want to see some reference papers, here is a survey paper published last year in Annual's Review in Control, and it contains a comprehensive list of references you can consult. And you can, I'd like to refer you, if you're interested, to this paper. So here is our approach. So we solved the optimization problem using dual decomposition, which will be presented after a few minutes. And there are some interesting features I'd like to talk about our algorithm. First, as I mentioned before, differentiability of the cost function or objective function, whichever one you like, is not assumed. Although it may be helpful to have a differentiable objective function, but we're not assuming that. We analyze the general case. And computations and communications of agents can be asynchronous, which again will be detailed after a few minutes. But the idea is that we allow asynchronous behavior of these agents, and there is no need to synchronize the network. And we prove almost sure convergence to the solution of the dual problem. So that's exact convergence to the solution of the dual problem with probability 1. It's not convergence in terms of expectations or convergence to the neighborhood. It's just almost sure convergence to the solution of the dual problem. And on the stronger assumptions, you can show some robustness results. That means when you have some errors in the system, we can show that it converges to the neighborhood of the solution. And the size of the neighborhood really depends on the size of the disturbance. And that's to be expected. And also on the stronger assumptions, we can give some convergence rate estimates, which is consistent with the centralized version of the algorithm. So now I'm gonna discuss the dual-based distributed algorithm and how it exactly looks like. So when you try to do dual decomposition, the first step you do is to write down the Lagrangian. So we have an equality constraint problem. So it's for each equality constraint, eij xi minus ej xj, we have a multiply called lambda ij. And we write down this Lagrangian, it's quite standard. And the corresponding dual function is to minimize this Lagrangian with respect to x. And note that this dual function is a function of lambda because you're minimizing over x. And one interesting property about this dual function is that it's guaranteed to be concave. And the proof is simple, and it can be found in standard textbooks about convex optimization, for example, the one by Stephen Boyd and Bert Seckers. And even if your objective function or cost function is non-convex, this one is still concave. So that's a nice property. And in this work, we're going to assume it's radially unbounded. So that means when the norm of the decision of the argument lambda goes to infinity, this function q also goes to infinity. And the dual problem is to maximize this dual function with respect to lambda. And notice that because we only have equality constraints, this problem becomes unconstrained. And we only have, again, since the cost functions are convex, constrained over a convex set with only equality constraints, we have the latest conditions hold. That implies we have zero duality gap. So the message is that if you solve the dual problem, which is maximizing this function q of lambda, then you solve the original problem, which is minimizing the big fx subject to the coupling equality constraints. So that's the message. You recover exactly the same solution. And one extra thing I'd like to discuss is about primal recovery. So what primal recovery is, let's say this big lambda opt is the set of solution of the dual function of the dual problem. Note that it's only a concave problem, so it's not guaranteed that we have a unique solution. So it's a set. That's why we have lambda opt. And you suppose you have already solved a problem. Let's say you get a solution called lambda star, and that's one solution of the dual problem. If you're just interested in the value of the function at the minimum, let's say fx at the minimum value of fx, then that's job done, and you just take the maximum value of q, and that will give you exactly the thing you need. But if in additional you want to find a primal feasible x, that is the local decision variables xi, that satisfies the equality constraints, then you still have to minimize the corresponding Lagrangian given this lambda star. So that's what we mean by primal recovery. So for a given lambda star, you can find some x star. Again, since you're only assuming convexity of the cost function, over this constraint set calligraphic x, there may be a set containing many possible x stars, let's just call it x star, that minimizes the Lagrangian. And because it's convex, so it's not guaranteed that for each local variable xi, they're going to satisfy the equality constraints. So that's going to be a problem if you want to really get the decision variable xi in the primal domain. So one way to solve this problem is to regularize it. So the idea is that a primal feasible solution is guaranteed if the cost function fx is strictly convex. So that's one key observation. And you can regularize the problem so that it's strictly convex. And the errors incurred by doing this regularization can be is in an acceptable range. So that's one way to cope with this issue. And if you're lucky to have some already strictly convex cost functions or even strongly convex functions, then it's not going to be a problem. So once you solve the dual problem, then you can minimize the Lagrangian. It's going to automatically give you a satisfactory primal variable x. So now, how we're going to derive our distributed algorithm. So note that we have a finite sum structure of the cost functions, which means that the corresponding Lagrangian or the dual function can also be written in a finite sum form. So the idea is that we write this qi lambda, which is to be assigned to agent I, that only contains variables that agent I has. So that is variables xi. So you remember we have those equality constraints that's in the form of eijxi minus ejxj. And we group everything related to xi. There may be some positive terms and negative terms to agent I, so that agent I can minimize this individual, let's call this individual dual function, so that agent I can minimize this guy locally without communicating with others. So, so the first point I want to make is that this infimum is taken over local variables xi, and let's say after minimizing this thing, you get one xi star. So that's the guy that's minimizing the local dual function. And one particularly interesting feature of the dual function is that this term eijxi star minus ejxj star, which is just substituting local solutions of xi star and xj star into the equality constraints, is one component of the supergradient of the function q lambda, because q is concave, so it's a supergradient. So it's the, if you're not familiar with the concave setting, so it's the counterpart of the subgradient of convex functions. So that is one component of the supergradient of q lambda, which means that if you can communicate with your neighbors, then let's say agent I talks to agent J, so that agent I has information of both xi star and xj star, then agent I has access to a component of the supergradient of the dual function q lambda, which means agent I can perform an update locally on a component of the dual function. So that's basically the motivation of our distributed dual algorithm. So it's an edge-based dual algorithm. How it works is that each agent minimizes this local dual function to get xi star, and it communicates with its neighbors, which is indicated by the coupling, then perform an update along the component of the dual function. So that's the key idea. And what roughly our asynchronous distributed algorithm looks like. So for simplicity, we write our algorithm in this form. So since it's a dual algorithm, so we're going to only present the algorithm for lambda. Here, lambda updates according to this formula. I'll explain these terms one by one. So lambda is the multiplier or the dual variable. Here, calligraphic A is a vector of step sizes of different components, alpha I. Here we allow different components to have different step sizes because they're controlled by different agents. They may not know someone else's step size, so it's possible that they use different step sizes. And this circle dot is just the element-wise product. So it's the same thing as you. So it's if everyone uses exactly the same step size, then it's just the standard form of. It's just becomes the same thing as you would normally see in the algorithm, where you have a step size alpha multiplied by some directions you choose. And as here labeled in red, that's the interesting part. So it's a block diagonal matrices with only 0 matrices and identities indicating the updating components. So if some components are updating, depending on the dimension of the components, then it's going to have identity matrices. And everyone else will have zeros, which means that they're not updating at all. So that's lambda plus equals to lambda. And they're not doing anything because they're not updating. And if it's identity, then they're going to, that corresponding component will be updated following this equation. And this G lambda, which is an element of the superdifferential of the dual function, and that particular element is derived from minimizing the individual individual Lagrangian to get this xi. So it's guaranteed to be one element. There may be some others, but we don't care. What we're interested in is just a supergradient of this form. So as I said in the previous slides, this one can be derived from minimizing a cost function locally and communicating with agents' neighbors. And here the vector E is some supergradient error vector. So since our supergradient is derived from minimizing some functions and communicating with others, so it's inevitable that we may incur some errors. So this E is just some error vectors that may come from quantization or not being able to minimize the functions exactly, etc. So there are multiple sources of errors, and it's abstracted in this single vector E. And here is an illustrative example. So in the synchronous case, in this case, let's just assume the step size is alpha and it's the same for every edge. Now we have a graph of 4 agents, so it's not a large scale. And it's very possible that you can do synchronous communication in this case. And in this case, the matrix S is just a 5-dimensional identity matrix because everyone is updating and it's labeled in red. So you just perform the updates of all components of the door variable using this form, and this supergradient, as I said, are of this form, which is derived from minimizing the Lagrangian. Now, the asynchronous case, things become a bit different. So there are 3 edges for whatever reasons they decide not to participate in this update. Maybe because they're not able to minimize their corresponding Lagrangians in time, so that they don't have the information available yet. Then if the network size is large, then it's costly for other agents to wait for them to finish their computations. So whenever you finish your computations, you can just perform update and do your things next. You don't have to wait for others. And in this case, the block diagonal matrix S becomes that's the diagonal elements. This one. So there are 2 1s and 3 zeros, depending on how you label the edges. So that's a rough idea of the algorithm and how the block diagonal matrix S plays a role in these algorithms. So that's the idea. And now we're going to analyze the convergence of the algorithm. So first, we're going to state some assumptions on updates. Although we claim that it's an asynchronous algorithms, but of course we can't allow it to be arbitrarily asynchronous. For example, if one edge has decided to sleep forever, then it's very unlikely that you're going to get convergence when you run sufficiently many updates. So we're going to make some assumptions that are relatively mild, I would say. So the first one is here is about how agents talk to each other to perform dual updates on the edges. So let's first define a variable gamma ik. So let gamma ik be the number of updates of component I. That's component I of the dual variable. Remember, this is a dual algorithm, so everything I'm going to talk about since now is going to be related to the dual variable. In the time length of k, that's the number of k updates in the whole network. And each component of the multiply is updated infinitely often, almost surely. So with probability 1, we have this inequality hold. So that means that when you take the ratio of this of the number of updates of component I, it has to be uniformly lower bounded by a number we call the big lambda here, which means that it has to be updated infinitely often, which is a reasonable assumption, because if one particular component, let's say you have a vector and you want to update its component by component, if one component has not been updated sufficiently often, then you may not be able to expect sufficient progress along that direction. So here, I would like to explain that K here can be viewed as a global timer. So as long as there is one update happening in the whole network, then K becomes K plus 1. So it's essentially a global timer. So which means that component I has to be updated sufficiently often when compared to the whole network. So that's the idea. And this assumption includes many popular stochastic and deterministic updating schemes. For example, in the literature of block coordinate descent for convex optimization problems, they often make the assumption that each component decision variable is selected with a strictly positive probability, and that's a special case of this assumption, and it certainly satisfies our assumption. Or they, in some deterministic schemes, they update every component in a round robin fashion. So for example, you have 5 components, you update in a fashion like 1, 2, 3, 4, 5, and like something like that. You just keep going like that. Or you update one component at least once in a finite number of times. Let's say n. N is finite, arbitrarily large. Then you have to update at least once each component in the length of n times. So all of these popular updating schemes can be satisfied. They satisfy our assumption. So it's a relatively mild assumption here. And next is the assumption on the step sizes. As we discussed before, we allow different components of ij to select different step sizes because they are different agents, so it's reasonable to do that. And for any components of ij of the multiplier, we have the following 3 assumptions. The first one is that the step size is squarely summable but not summable. So it's a standard assumption of step sizes when you have cost functions that are not that do not have Lipschitz continuous gradient. And if you are familiar with subgradient algorithms in convex optimization, this is a very standard assumption if you want to get exact convergence to the solution. So that's a rather standard one, and we require every component to use step sizes that satisfy this assumption in order to get exact convergence to the solution. And the next two assumptions, although they look complicated, but the essential idea is to ensure that even if you're using different step sizes, even if you're updating with different frequencies, they have to have similar progresses. So that's to ensure that the progress along different components are in the same order. So I'll give you some examples about this later, just in the dot points below. So here, different from the K I used in the previous slides, here M is shall be just viewed as indices of sequences. So they're not timers. So they're just indices of sequences. It's got nothing to do with timers, so that should not be confused. And the last 2 items ensure that progress of all components are in the same order. So I'll give 2 examples to illustrate this. So an example, a good example that satisfies this assumption is the standard step size, which is commonly seen, is of 1/k. Here I use m+1 to allow a well-defined step size when m is equal to 0. And this Ci can be selected as long as they are positive and finite. They can be arbitrarily chosen by different components I and j. And that's a good example, and it satisfies all 3 items of the assumption. And here is a bad example, and that's something we want to prevent. So you select, let's say you have 2 components, I and j, and a component I decides to use this very well-known step size, 1/k type, 1/m+1. So that's 1, 1/2, 1/3, etc. And someone else, they want to use, let's say, larger step sizes. So they use 1/m+1 to the power of 0.8. So this one is also squarely summable, but not summable. But the problem is that when k goes to infinity, even if the algorithm is synchronous, if you take the ratio, depending on whichever one you put on the numerator, you either get infinity or 0. So that's not the thing we wanted to happen. So this means that the one with larger step sizes will have infinitely more progress compared to the one using the smaller step size sequences. So that's something we want to prevent. We want to ensure that every agent selects step sizes that will give you similar progresses. And they can be different, subject to some ratios, Ci. It can be anything, can be a billion, as long as they're finite, then it's okay. But definitely they can't be infinity. And that's something we want to rule out by these assumptions. And another thing I want to discuss is that even if you choose identical stepsize sequences, this may still lead to stepsize mismatches depending on how the block diagonal matrix S looks like. So here is an example. Let's say every component uses this commonly used 1/n+1 sequence. That's the stepsize sequence you like. Let's say we have two components, 1 and 2. And so that means that A0, which is the vector of stepsizes, they're all 1s. So that's 1, 1. And if S0, that's the block diagonal matrix at time 0, if it's diagonal 0 and 1, which means that component 1 is not updating and remains unchanged, and while component 2 updates, then the step size at the next step will be 1 and 1/2 transpose. So even though they're using identical step size sequences, the step sizes they're using at updates may still be different. If all of the communications and computations are synchronous, which means that S is identity, then we recover the synchronous case, which means that if you select identical step size sequences for all components, then you're gonna get exactly the same step sizes at each step for each component. So that's one thing we want to mention. Even if you choose the same, you choose identical step size sequences for all components, you may still have step size mismatches. So lastly, the assumptions on the supergradient errors. So it's a quite standard assumption here. We assume that the supergradient error satisfies these two inequalities. It's zero mean and has bounded variance by this constant k. And we're also gonna assume that the supergradient estimates used in the updates are bounded. So the reason why we need the second assumptions is that when we prove the convergence of the algorithm, we use tools from stochastic approximations. So especially in particular, that's ODE methods in stochastic approximation. So if you are familiar with tools from stochastic approximation, one of the key assumptions in those methods is that they're going to assume the iterations are bounded a priori so that it will not blow up. Then you can get convergence properties. So in our case, combined with other assumptions, so it's a bit technical, it turned out that if you can guarantee that the supergradient estimates are bounded, then we can get the iterations are also bounded. So it's not a straightforward result, but combined with other assumptions, we can show that. So that's why we need the assumptions here. So it's essentially to guarantee that the iterations are bounded. Since the supergradients we'll be using comes from minimizing the individual Lagrangians over the constraint set X. So if you're lucky to have a compact constraint X, then it's guaranteed to be satisfied, this second item of the assumption. And in fact, in most cases, having a compact constraint set X is not a particularly strong assumption, because in order for an optimization problem to make sense, you often, to make sense and have physical meaning, it often makes sense to have a solution that's real valued and does not become infinity. So constrain a compact set whose size may be arbitrarily large, I would say it's a reasonable assumption. So it's not a very strong assumption regarding the supergradient of the dual function. So here is the theorem. So let lambda k be the dual variable at time k, and lambda opt be the set of solutions of the dual problem. And under the stated assumptions, lambda k almost surely converges to this set lambda opt as k goes to infinity. So that's convergence with probability 1. So with probability 0, you're not going to get a convergence. So that's, if you're not familiar with probability theory, then it's just one way of saying it's very, very unlikely that you're not going to get exact convergence. So that's the main convergence theorem. So here is the proof sketch. The proof is a bit technical, so I'm not gonna present the full proof here, but I'm gonna present some ideas we use in the proof. As I said before, the proof is based on ideas from stochastic approximations. So the first step we do is that we linearly interpolate the discrete time variable lambda k to get lambda bar t that's piecewise linear in time. So after this interpolation, we get a function that's continuous in time. So now this lambda bar is a continuous trajectory that's continuous in time, and lambda k can be viewed as samples from this continuous function lambda t at a certain time instance. And in this work, we choose to linearly interpolate this lambda k, and that's not the only way to do it. You can also interpolate the functions using other approaches, but the idea of the proof will be very similar. And the next step is that in the limit, we can show that this continuous time function, lambda bar, almost surely satisfies this differential inclusion. Here, it's the different, how it's different from the standard supergradient flow is that there is a coefficient matrix big theta t in front of the supergradient, in front of the super differential partial q here. So what this this matrix theta t is that this theta t captures the synchrony of the algorithm and stepsize mismatches that I discussed before. So for example, different agents may update using different frequencies, and this progress really depends on the step size at the current step of different components. So if they're different, then when we interpolate the time, when we interpolate the discrete time decision variables lambda k, we use the biggest step size currently used in the update as the time. So for those components that are using smaller step sizes, then the progress of that particular component may be smaller, and it's captured by this coefficient matrix. For example, in the example I showed you before, if someone is using step size 1, the other one is using step size 1/2, then this for this matrix theta t, one element will be 1 and the other would be 1/2, indicating different progress along different components. And one interesting thing we can show is that under the stated assumptions, we have that theta t is positive definite, and in fact, it's uniformly lower bounded by this epsilon I, and epsilon is a positive constant that depends on some of the parameters I showed you in the assumptions. And once you have these conditions, you can use Q minus Q star, which is the solution, as your Lyapunov function, to show that for the differential inclusion here, in the second bullet point here, the set lambda opt is uniformly globally asymptotically stable. That's U guess. So that's stability proof for this super differential for this differential inclusion. Since we show that in the limit, the interpolated trajectories follows this differential inclusion, so you may expect that the discrete samples lambda k also converges to lambda opt, which is U guess. So that's the result that stochastic approximation tells us. So that's how we prove the result. And next, you may wonder, once if the supergradient error is not zero mean, for example, it's norm bounded, and in fact, it's very likely that it can be norm bounded. It may be some noise or induced by some adversaries or coming from some other sources. And you may be interested in asking the question, can you show similar convergence results under these conditions? And the answer is yes, if you're interested, if you're okay with convergence to neighborhood. So if the expectation is non-zero and it's not bounded, we can show that, so here is a typo. We can almost show convergence of the dual variable to a neighborhood of the set lambda opt. And to show this, we need an additional assumption on the step sizes. So in stochastic approximation literature, this assumption normally is called the balanced step size. So the term balance refers to the essential meaning, to the essential point why we need this assumption. So you can see that I replace the limit inf and limit sup by the limit, and the ratio becomes a constant Cij. And in the original paper published by Borka, when he proposed this balanced step size for the first time, he assumes that all of theseCijs are 1. And that simply means that although they're using different step sizes, they all have exactly the same progress when the time goes to infinity. So that's what balanced step size means. And one example is that you choose Ci over M, and you choose this type of step sizes for all components, and it's going to satisfy the assumptions. Even if they're not synchronized, updating with different frequencies, as long as the updating scheme satisfies the infinitely often assumptions we stated before, then it satisfies this balanced step size assumption. And why we need this assumption is that we can get, you remember in the previous slide, the differential inclusion is non-autonomous. We have a coefficient matrix that's time varying. If you're using this balanced step sizes, we can show that this theta t is actually a constant matrix and it's positive definite. In the original work of Borka, if all of theseCijs are 1, then this theta t becomes identity. So the limiting differential inclusion becomes the standard supergradient flow or superdifferential flow. So if you have these assumptions satisfied, then this theta t becomes a constant. So that's the key message of this assumption. And why we need theta t to be a constant? That's from robustness result from continuous time systems, because Q is a concave function, and it's automatically can be shown that the superdifferential is outer semi-continuous. So that's enough regularity we required for the stability property of lambda opt to be robust. So if theta t is constant, then the supergradient flow, the U-gas property of regarding the supergradient flow, U-gas of lambda opt is robust. So what that means is that lambda opt is semi-globally, practically, symptotically stable for the perturbed supergradient flow. So if you have some errors, depending on the size of the errors, you may have convergence to a neighborhood of lambda opt, and the size of the neighborhood depends on the size of the error. And you, instead of global asymptotic stability, you may have now you only have semi-global stability properties. And the region of attraction, again, the size depends on the size of the error. So since we have already shown that the interpolated trajectories, the interpolated discrete time decision variables satisfy this differential inclusion, we can state similar results for that. So the theorem is stated below. Suppose that for any delta E, for any positive delta E and big delta E, there exists an epsilon E such that the norm of the expectation of the supergradient error is bounded by this epsilon E for all k. And lambda k belongs to this set, so it's a ball. This notation means a ball centered around the origin with radius big lambda E. And this lambda k is contained in this set infinitely often. Then we have that when k goes to infinity, so again, k is the global timer, lambda k, the distance between lambda k to the neighborhood of lambda opt, whose size again depends on delta E, and the distance goes to 0 almost surely as k goes to infinity. So what it means is that for any given delta E and big delta E, you can find an upper bound on the supergradient errors so that lambda k converges to a neighborhood of size delta E of the set lambda opt. So that means that if the bound on the norm of the supergradient error is sufficiently small, then you can converge sufficiently close to the set lambda opt, and this big lambda E can also become sufficiently large. So when this epsilon E goes to 0, then it converges to the set lambda opt, which recovers the previous theorem we stated in the previous slides. So that's the message. Again, these parameters delta E, this small delta E and big delta E, they depend on epsilon E. So the performance of the algorithm really depends on the size of the supergradient. If the environment is very noisy or you have a very poor computation devices, then which means that epsilon E may be very large, then you may not expect to converge to a neighborhood that's a satisfactory neighborhood that of lambda opt. So that's the message. So one drawback of using tools from stochastic approximation techniques is that it doesn't give you a direct convergence rate estimate as done by using tools from convex optimization. And this convergence rate is often of interest in many optimization problems. So we also did some investigation on these issues. And in order to do this, we assume that all components use identical step sizes during any update. So here, what we mean by identical step sizes during any update is that when any of the components are updating, they are using the same step size. For example, if you have 5 components and components 1, 2, and 5 are updating, and if one of them is using step size 1/4, then everyone else that's updating now would also use 1/4. And the step size should also satisfy the standard assumption. Since we now require everyone uses the same step size, so you just need it to be square summable but not summable. So that's the assumption we need. That's standard in convex optimization literature. And since we're using diminishing step sizes for general concave functions without Lipschitz continuous supergradient, we may only get sublinear convergence rate. And if you're interested in accelerating the algorithm, you can make some additional assumptions. For example, one interesting result in duality theory is that if the objective function, I mean, the big fx, if that's strongly convex and has Lipschitz continuous gradient, then the dual problem is also strongly convex and has Lipschitz continuous supergradient. And in that case, you can use constant step sizes to accelerate the convergence rate. But that's not the focus of our talk. We are focusing on this general case. So we use diminishing step sizes for general concave functions. And we show that the best achievable rate is of order 1/√of k. And that's consistent with the centralized version of the algorithm. And again, if we decided to use 1/k type step sizes, and you can also show that the convergence rate is of order 1/log k. And again, that's consistent with the results in centralized version because we're also using tools from optimization literature. And here we're not using any ideas from stochastic approximations, which means that the assumption of bounded iterates can also be relaxed. So we allow the supergradients to be upper bounded by some term that depends on x. So it's allowed to grow to infinity as x goes to infinity, as the decision variable lambda goes to infinity. So now I'm going to discuss an illustrative example. So we consider the problem of minimizing this function fi, the sum of 50 individual functions using 50 agents. And each fi is given by these unnormalized entropy functions. So here, each pi is randomly generated. So it's a positive number to make sure that this function is well defined for positive x. And note that this function is strictly convex. So if you solve the dual problem, then you can minimize the individual Lagrangian to get this x, and it's guaranteed to be feasible. Note that here x is a scalar, so we don't have those selection matrices EIJ and EJI, and this is actually a standard consensus, optimal consensus problem, which means that you after solving a dual problem, using the multiplier you get and solve this individual Lagrangian using the resulting lambda star, you're automatically going to get xi's that reach consensus and minimizing, or at the same time minimizing this function big fx. And we test this, we run our algorithms under 6 different settings. We want to compare different things and compare the impacts of different settings on the convergence properties of the algorithm. So first, we run the algorithm using 2 different graphs. The first one is a random graph shown here. So it's of 50 nodes and 348 undirected edges. The other one is a path graph. So if you don't know what path graph is, so it's 50 agents, and with each agent it's 50 agents with 98 edges. So that's a connected graph with the least possible edges. So in topology, it looks like a line, but it's a path graph. And we want to test how much we lose in terms of convergence rate when we run this algorithm asynchronously. So we compare this algorithm to the synchronous algorithm. So that is, when you perform an update, every single edge perform the update synchronously. So that's a purely synchronous algorithm. It's just for comparison purposes. So for this synchronous algorithm, it's a standard centralized version of concave optimization of the dual function. And next, we'll compare the performance of the algorithm, of the asynchronous algorithm, on the local step sizes and global step sizes. So what do we mean by local step sizes? So local step sizes means that agents or edges update their components using their local step sizes without any coordination. So that's the example I talked before. So you may have when component 1 and 2, suppose they use exactly the same step size sequences, at any time instance, they may update their corresponding dual variable using different values of step sizes. So it may be 1, and while the other using 1/2. And then the other setting is global step sizes. So that's one we use when we derive convergence rates estimates. So whenever there is a subset of edges that are updating, they have to use the same step size value. So the step size we use in this experiment is 1/n+1 to the power of 0.7. And it's identical step sizes for all edges. And remember, in the asynchronous setting with local step sizes, the edges that are updating may use different step size values, although they're using identical step sizes sequences. So here is the performance. So you can see that all 6 curves, they all have sublinear convergence rate. So it's the absolute value of the difference of the dual function at the current iteration. It's the difference of the dual function at the current iteration with the optimal value function, Q lambda star. So lambda star is the solution and Q is the maximum of Q. And you can see that the one that converges the fastest is the one in cyan, so down the bottom. So that's synchronous update using random graph. So that's the one with many more edges than the path graph. So it's intuitively, it should be expected like this because it's synchronous and you perform much more updates along the edges compared to the asynchronous case. So no wonder they are the fastest, but
Yankai, sorry, can you wrap it up in 2 minutes?
Okay. So that's the fastest. And one particularly interesting feature is that you can see that the 3 lines down the bottom, they're all using random graphs. So it seems like, although not explored theoretically in this work, the graph with more edges seem to help accelerate the algorithm to some extent. And that's an interesting thing to be investigating in our future work. And if you're interested in how the consensus progresses in the primal domain, here is a plot. You can see that the 3 plots using past graphs, after 5,000 iterations, the progress of consensus are still not clear. There are still discrepancies along the 50 agents, while for those updates using random graphs, the consensus, you can clearly see that when K goes to 5,000, they almost reach consensus, at least graphically. So it shows that the graph with more edges heuristically can help accelerate the convergence of the algorithm. And now I'm going to conclude and present some future research directions. So we have developed an asynchronous distributed algorithm based on dual decomposition for a class of convex problems, and we utilize the finite sum structure so that dual decomposition gives us a distributed computation. And the asynchronous algorithm is analyzed as a block supergradient update of the dual function, and its proof is via ODE approaches from stochastic approximation. And then we almost show convergence to the solution of the dual problem on the relatively weak assumptions, both on the step sizes, on the cost functions, and on the updating schemes. And a simulation example is provided to illustrate the main result. So here are some future research directions. One thing of particular interest is the tools for convergence rate estimates. We are obviously interested in convergence rates, even you are using uncoordinated and local step sizes. And we want to theoretically explore how communication graphs impact the convergence of the algorithm. It seems that more communication links can accelerate the algorithm, and we're trying to show if that's really the case theoretically. And the last one is to extend this work to other classes of problems. For example, things coupled via inequality constraints, and for example, in some online setting where the optimization problem is time varying, and it's very interesting to see how the algorithm behaves in those settings. So that's all for today. Thank you for listening and stay safe.
Okay, thanks, Yankai. Now let's see if I have any questions here. Does anyone have any questions for Yankai? Okay, Emilian has a question. So unmute yourself and ask your question. Emilian?
Yes, hi,
Yeah.
thanks. So I have 2 questions. The first one is, so you talked about the connection hypothesis on your graph, that it is a classical assumption. And I don't see where, do you have one in your list of assumption? Because I don't see where it is exactly.
You mean the assumption graph?
Yes, we have, yeah.
So it's not formally stated in this form, but we mentioned that in the setting. So here we mentioned that n agents connected via a network described by an so it should be connected. I didn't mention that. So it's connected and undirected, because you need to communicate your solutions to the local problem to your neighbors, and then you'll get the updated dual variable back to perform to solve the new individual problem. So that's the assumption on the graph. It's sort of standard.
Okay, but it isn't. But is it important in your step size choice, for example, or something like this? I mean, is it something that matters in your algorithm?
We're not using like any coefficients of the network. For example, the second largest eigenvalue or the connectivity coefficients of the graph. So we only require it to be connected and undirected. And the step size doesn't really depend on the graph. So there.
Okay, thanks. And a second question about your robustness theorem.
Yep.
Does your step size, the step sizes, depend on the epsilon error? Yeah.
No. Step size is pre-chosen.
Okay.
And so you just choose your step size sequence and initialize it, and then let it go. So each agent can decide how the step size updates by its own local clock, and then that's it. It doesn't really depend on the size of the disturbance.
Okay. Okay, thanks.
Okay, thank you.
Thanks, Emilian. The last question, Alejandro is going to ask the last question. Alejandro, just ask, please.
Depending on the updates, right?
Can you speak louder? I can't really hear.
Do you design that S in order to satisfy the assumption, or is it given?
Sorry?
The question was that, do you design S, or S is given to you?
This S, here we present the algorithm in an abstracted way, because in the work we submitted, the algorithm is presented in a much more complicated form. Here, S indicates how different components are updated, and it's captured via this assumption. So
yeah, I know. Do you design it to satisfy the assumption, or how do you construct it, or is it given by the network or whatever?
yes, you have to design a network to satisfy this assumption.
No, it's given by the network. You can ask the other question as well. Yeah.
Okay, thanks.
Okay, thanks everyone, and thanks Yankai again. See you again, all of you, hopefully next week for our next talk. Thanks.
Thank you, Iman.